different labs which are mentioned here. And they also, in addition to like CSIR and this, they also promote NGOs. But all NGOs should have at least a record of at least 3 years. That 3 years of successful working, those NGOs also can approach them for getting funding from them. And also they support, they support different projects from different agencies, including government agency, non-government agency. But they are actually the requirement. Normally the requirement is that if the project is submitted to them from either any agency, if they have an industrial partner with them, which may not be providing directly money to the project, but in kind, if he is supporting the project, then that gets the priority. That type of embargo is there with the DEIT laboratories. The Department of Atomic Energy, they also support research and development. Again, to all, as I will repeat, but they have two major funding agencies, that is Board of Research in Nuclear Sciences, BRNS, and another is BRFST, Board of Research in Fusion Science and Technology. So these two agencies are the major agencies which support projects. BRFST basically is for the projects which are directly for the fusion technology, but BRNS supports all type of projects. In addition, like others, they also, like DE also, they support projects from their own projects, because they also run their own major projects, so they provide funding to the different agencies. DST is a Department of Science and Technology, is a major source of providing funding to the all types of, this is basically not, I'm talking electronics or physics, all types of, all sciences, all streams of sciences, the funding is provided to them. They also, not only they provide funding to the projects which are submitted by different agencies, but they do also support the for carrying out the symposium seminar, or also support for the international travel. Only thing, you should have a good academic record, good papers which we are going to present, is a quality project paper is there, then you are likely to be funded. Maybe you may be from academic institute, private institute, government institute, is no bar. Only thing is, you should have an exceptional working record, so you get funding for participation in various conferences, etc. But DST have a number of schemes. I am not going to detail. If you go to their website, you will find number of schemes which are available to youngsters for carrying out research in the field of science and technologies. And of course, this INSPIRE program, as you know, this is again is for it. It's a major program. It starts from schooling, it goes to the INSPIRE Fellow. If you are selected as INSPIRE Fellow, you get a fellowship of 72,000 rupees. That's the, and from the 10th level, they select like that. So the INSPIRE program is also running for the last 7-8 years now. It's a very major program of DST for youths, particularly there. Now coming to the another 10 minutes, 15 minutes or so, I'd just like to give you a glimpses when we talk of communication. Of course, it has already been covered by Professor Chakravarti. These are microwave devices. The devices which go into communication start from very low power. When you talk of milliwatts of power or 1 watt of power. When you talk of cell phones, the power requirement is very low. Frequency is very low. It is 1 to 2 gigahertz only, and power levels are also very low. It's at the most 1 watt, or less than that. But there are the requirements in the communication sector, in the defense sector, other sectors, where you need very high power of the order of megawatt and gigawatt of power. So naturally, there you have to go to vacuum-based devices, which can give you that much high power. This gives you an idea in terms of if you see the frequency and the average power capability. So all this top, what you see are the based on vacuum-based devices. When you are talking more than megawatt of power, and these are the graph. Sorry, west band impact. These are the lower one. It shows the capability of the semiconductor devices. So the problem is there actually, the power level are limited. Also the frequency extendability is also limited. But as on today, as some idea was given by Dr. Chakravarti, new materials have come up, the indium phosphide, gallium nitride. These are materials which have, in addition to the silicon and germanium, gallium arsenide, so new materials are coming up which have increased the capability of these devices. So in the future, the curve, what you see here, naturally it will go this way as well as that way. So that is the future of this there. And in addition, the advantage of semiconductor devices is you can combine n number of devices without very much loss of efficiency. So you have a 1 watt device, you can count 1,000 devices you can combine to get 1 kilowatt power out of that. So that is not possible with a vacuum-based device. Limited numbers, 2 or 4 or 5, you can do that, but not more than that. But that you have that capability there. And I like to add here, I don't know what is the next actually. This another thing I like to share actually. If you talk of very high frequencies, going to terahertz, the requirements are now extending to terahertz. So part of it he was telling about 95 gigahertz system for that security purposes. But there are systems which are going up to 1.4 terahertz or even more than that. Systems are there, particularly for imaging and for medical applications. So the future is the terahertz devices have a long route to go, and there the marriage of microwave devices and semiconductor devices is must. Because as on today, microwave tubes which are based on vacuum technology cannot go beyond 100 gigahertz. Conventional microwave tubes, I'll say. There are fast wave microwave tubes, no other gyro type devices, they can go up to 1.5 terahertz. They are there, but they're different. But normal microwave devices like klystron, magnetron, traveling wave tube, backward oscillator, they have limitation of power. You can go up to 95 gigahertz or 100 gigahertz, because beyond that, the size becomes so small, it is very difficult to fabricate them. In addition to that, the power is also limited, because the size of the structure shrinks, so it is not able to dissipate that much power. So that limitation is now actually we are talking into where we are two steps are being done. One is where the as a device, the microwave device and semiconductor device, they are combined in one box. For a user, it is just one box, feeding one input, getting output. But within that box, you have a microwave device, vacuum-based device, you have a solid-state device. So that is known as microwave power module. So there we are combining the two devices. But further step, when we are talking of the terahertz devices, there actually you have to combine the technologies. Because semiconductor technology, you can fabricate structures going into tens or hundreds of micron, where it is not possible through the normal route. So you have made those structures using the semiconductor technology. Dr. Suchinder Pal is here, maybe he will go through some light on that. But that is actually. And then similarly you need a source, because your output depends on the input. Your cathode is not capable of giving that much power, so how you can expect a power output? So naturally the limitation of the normal microwave tubes is the current density of the cathode is limited. At the most you can go up to 100 amperes per square centimeter. That limits your output power. But there are now, using the semiconductor technology, you use field emitters. So with the field emitters, you can have kiloamperes per square centimeter current density is available now. So the future is actually, when we are talking of actually terahertz devices, the future is for combining the two technologies. This just show you what the devices which go into the actual space with the satellite. They use the traveling wave tube as also use a solid state amplifier as well as a klystron based amplifier. So this just shows the comparison in different frequency bands. You see the traveling wave tube still has they are better better in comparison to semiconductor devices. Basically to the reliability, because they are actually very important. Not required. Not required. This also has been covered, but just say this is there, so you can see how the communication we do through microwaves, because microwave penetrate that ionosphere, and they go to the satellite, and the signal comes, and for the lower frequencies you have the direct wave and reflected. That way the communication through troposcatter, through ground waves, it is possible. But actual microwave, because they penetrate the surface of the earth, they move in the straight line. So they penetrate the atmosphere, they are not reflected by the atmosphere. So with that. Already been covered. Other applications have already been covered. Then here actually, what the requirement of communication sector? We need moderate RF power, gain of 50 to 70 dB. All these specifications are there, particularly for communication tubes. And when it goes to the space communication, there actually the life is very important. There we are talking of 15 to 20 years of life. So your device should work for that particular life. It has to be very reliable. It has to withstand all those shock and vibration during the launching. And also, it has to be highly efficient and also the low in weight. So these are the special, in addition to normal communication TW, these are specific requirements which are coming from the devices for the space sector. There are the various organizations which are involved in this communication devices. These are the various frequency band where the lights are there. This is what we have been doing at Sri Pilan with the support of ISRO, both at SAC, Space Application Center, as well as ISAC at Bangalore. We have been making space qualified traveling waves. We already made. Thank you. I am having this problem for the last 10 12 days. I have come here, there is a lot of resistance from my family. Why you are doing? But anyway, so this is what we have already made. We have already transferred. This was the. This is the KU band TWT, which is being made at present with the support of ISRO, and this is what we have already made for ISRO. The very first on the top, what you see, traveling with you. That was for the ground application, not for space application. That was with used with the Space Application Center at Ahmedabad, as well as at Earth Station at Delhi. These devices were actually used in their systems. There are the different other devices which have been developed by our institute. This is what you see is this one is the actual traveling wave tube, which has already been completely developed and it was meeting all the requirement of ISRO, and they have already been handed over to ISRO. And these are the other one. The other one, what you see here on the sorry. This is the one which is being developed with the 2 frequency band we are working on, again with the support of ISRO on this. These are the klystrons which I have developed for communication purposes as well as for other applications. Their requirement for this very first was the klystron what you see here for troposcatter communication. And this particular 2 devices, one is 5 megawatt, the other is 6 megawatt. The length of the tube is about 1.7 meter. And the weight of this particular tube is around on the extreme right, around 175 kg. In addition to that, we are also making another class of device I have not shown here. That is the gyrotron, which is about, at present the device is about 2.5 meter and the weight of the device is about 200 kg. In the next generation which you are going to make, it should have a length of about 5 meters and we can imagine the weight also. So that's the gyrotron we have been working on that. I have not covered that because that was not for communication. These are the various, just as advocate for our institute, these are the opportunities which are available to the youngsters in our institute as well as in other labs of CSR and as well as in other R&D laboratory of DRDO, DAV, everywhere such similar slightly different type of programs are available where we have this these are the various project positions we have. We also provide 6 months to 1 year training to the MTech, but we prefer 1 year MTech program training. And also we have this scientist fellow positions, different, because for these positions you should have a bright academic career. And in addition to that, the RFSRF, we also project positions. At present we have about 125 such positions which are going on. And the different levels of students with diploma, BE, Tech, MEM Tech or PhD, they are admitted inside program. But only thing they are with the projects, depending on the tenure of the project, normally to 3 to 5 years. In addition to that, we have this. We already covered this. We have this scientific position. We have this academic position. We have the integrated PhD program at these 3 streams. What I'd like to conclude that there are a lot of opportunities for you youngsters, particularly for pursuing R&D. There are opportunities in the country. They are available. Only thing is you should have a zeal of working in R&D, and a lot of scope is there. Now things have changed. Economy of our country has changed. When I was of your age, there were no facilities was there. It was hardly to get any equipment from major agencies. So now, as on today's situation, is very, very good. You get support. All type of support is available. Lot of money is available. Only thing you should have interest in carrying out R&D. Thank you very much for your patience here. Thank you. Sorry for this.
Thank you, Dr. Joshi, for a very interesting presentation. So informative and so lucid and so comprehensive. And I think this was a lot of information for the youngsters to get themselves involved in research area which is connected with microwave tubes. So if there are any questions from anybody, I think Dr. Joshi would like to answer. Any questions?
We have something from youngsters, not from the... आपको पूछना चाहिए कुछ जवाब आएगा तो दूंगा तो नहीं दूंगा पूछना तो चाहिए भाई पूछना चाहिए जरूर should ask some question.
I think they are a bit hesitant to ask in a group of this type. I think over lunch they would probably have many more questions.
My mail ID is there. You can.
So you can write to him, or over lunch you can ask him any questions.
Thank you very much. Thank the organizers once again.
So we have the third speaker of this session. This is Dr. S. Pal. He belongs to and institutions which are very well known, same as Dr. S.N. Joshi's. His research achievements are outstanding, 16 years of research experience in the areas of integrated optics involving the design and technology development of various specific photonic components, gallium arsenide gallium arsenide material based LED devices and waveguide gratings. 80 scientific and research papers on various national and international conferences, and awarded Commonwealth Scholarship in the University of London, acted as a reviewer of various national and international journals, and he is a member of the Institute of Physics, Optical Society of India, then IET, and Indian Physics Association and Semiconductor Society of India. So I think we are all very keenly looking forward to the talk of Dr. Pal on a subject like basic integrated optical devices for communication and sensing, an overview of design and fabrication. Such an area of such a contemporary interest. I would like to invite Dr. Pal to deliver his lecture. Dr. Pal.
Thank you, Chairman, for the introduction. And I also thank the organizer to invite me and giving the scope of giving the lecture on this topic. And I have organized this lecture particularly in a fashion so that researchers, PhD researchers and PhD researchers are motivated to work out in that area. And also I thank to Dr. Joshi that he has already introduced CSS CD and remarking about possibilities of merging of the microwave tubes and semiconductor devices. However, I have identified particularly the passive components devices for the communications and sensing, not active devices particularly in this. So I start my presentation with the title Basic Integrated Optic Devices for Communication and Sensing. I will look forward for overview of design as well as fabrication. So these are the outlines, fundamentals of some integrated optics and integrated optic devices. Why I have chosen optical power splitter, multiplexer, demultiplexer, and waveguide gratings, because these are the three major and basic components, passive components, with which we can go for any type of circuit combinations in optical systems. then some of the devices that have been fabricated at CSIR series and future trends, and I will conclude my presentation. Before start my presentation, I just show these are the optoelectronic devices group, including scientists, project staff, student trainees, although this is an old picture, but this shows some of the present workers as well as past workers. So whatever I will present, particularly for the fabricated devices, this is the contribution from all the group members. So you see, these are the basic photonic integrated optic device, passive devices and components made by this type of structure. That may be planar light wave structure, that is, sorry. That may be buried structure. It can be converted into channel waveguides, optical fibers. It would be just similar to cylindrical waveguide type of structure. And in the lower part, that is the hybrid type of structure, including all the waveguides, modulators, source inbuilt sources, and fibers are connected to the outer world. So, what are the basic goals and status, particularly for integrated optics? Mainly to miniaturize the optical devices. At the same time, we have to go for as best possible of optical integration within that devices. And for the status wise, it is very much lagging behind, particularly for the circuitry from the electronic counterpart. But as far as the basic functionalities are concerned, few commercial devices are available, although research interests are growing on, particularly for optical integrated circuits or planar light wave circuits, including or without including the circuitry. See, this is the wavelength or frequency spectrum, and in this spectrum, this is the usual optical window. In this frequency range, the optical communication particularly we are interested. So starting with the basic structure of the slab waveguide, the basic principle is we have to have core and undercladding and overcladding. And the refractive index of the core should be higher compared to the bottom cladding and top cladding, so that whatever the signal is being propagated through the core, that will be propagating through that guided region through the internal reflection. But depending on the requirement, we can choose for the top cladding and bottom cladding material as well as the refractive index, so that it may happen in this way, that total internal reflection of the third condition, like that, in both top cladding and bottom cladding refractive index interfaces, the total internal reflection occurs, or the total internal reflection happens only in the top interface, so that substrate cladding radiation may be possible, particularly for different sensing applications. So particularly for communication, these are the basic structure schematic. We use laser as a source, we use optical fiber or optical waveguide as medium and receiver as detector. And when we transmit some signal in digital form, and after transmission it is deformed in that fashion, particularly for the attenuation or loss and dispersion. And at the end of the receiver, we want to have minimum intersymbolic interference, so that eye diagram should be prominent enough. So for that, we need to minimize the attenuation or loss. At the same time, we need to minimize the dispersion also. But particularly in this presentation, we will discuss the planar light wave circuits and planar devices. Particularly for these devices will be required for integration type of things, not for the propagating in long haul. For long haul communication, obviously the medium is optical fiber, but wherever the integration is required, some splitting is required, some signal processing is required, we will use those integrated optic devices. So as I discussed, these are the basic structures. Maybe strip type devices, embedded type strip, RIB type of or RIS type of structure, strip loaded, channel type of structure, and that is depending on this type of refractive index contrast. And there are various types of waveguides: straight waveguide, bended waveguide, splitting waveguide, magenta type direction coupler. Those can be used depending on the requirement of the device or the system. And these are few particular three-dimensional waveguide structure, and these are the requirements. For example, straight waveguides we require for single mode propagation. Whatever we discuss, we consider the single mode propagation, particularly for designing of single mode waveguide. That itself a very much interesting, and that is very much required, because particularly for long haul communication we don't need multi-mode, because to avoid the mode interaction. Similarly, for corner bent waveguides, for changing the optical path direction, bent and S-type waveguides, so this is also for changing the optical path with smooth transition. Tapered waveguide, that is for smooth expansion of the waveguide without mode conversion, because if we extend the waveguide width and thickness, that may go for multi-mode, but if we design properly, so smooth transition of waveguide dimension is possible without mode changing. Similarly, branching waveguide, that is required for dividing and combining of optical power. Crossed waveguide or directional coupler, particularly for required for distributed mode of coupling. So now I have completed the fundamentals of interior optics. So we'll discuss the optical splitter, multiplexer, and waveguide gratings as basic integrated passive components. Why I have chosen? For example, there are a number of wavelengths we want to transmit. So we have to combine this, so we need coupler. And for this coupler, we can use multiplexer. So that's why I have chosen multiplexer, demultiplexer. After combining these wavelengths, suppose we want to split that power in various components with even or uneven power. So we can use a splitter, that's why I have chosen splitter. And after splitting, power is divided, but wavelengths are combined. So again, we have to filter out. So that's why we have to choose some filtering in terms of bandpass filter or some other filter. So for that purpose, we can use waveguide gratings. So first is optical splitter. Whatever we discuss for the single mode propagation. So this is the typical schematic. That single mode is coming and then smooth transition by expanding this tapering and then going towards to branching. So it can be, the concept can be determined from the optical fiber also. Suppose we have optical fiber, two optical fiber, so signal is providing suppose in that direction, and some portion of the energy will be coupled to the cladding. So suppose if we polish that cladding to some extent, so that more energy will be coupled to the cladding, that region, and after that if we fuse these two wave fibers, then the signal is providing in that direction, so portion will be coupled in that way, in that waveguide as well as in that waveguide. But that is depending on the tapering angle. What is that angle? Coupling zone, that means this length as well as the thickness between the axis of the two cores. But this is very much dependent on the wavelength. So that's why if we go for that splitting of the signal, we can go for this type of structure, symmetric Y type of structure, where this is not wavelength dependent. Suppose we want to go for 1x8 type of splitter, particularly this is used, this can be used for cable TV operations, particularly now it is fiber optic cable is used, and that's why lasers are the driving power. So one particular laser, if we want to use, so for every cable TV operation, it is not desired to use every individual laser. So we want to split the power. So in that case, maybe 1x8 or 1x16 splitter are the useful devices. And if we design in that fashion, so this goes to that expanding of that waveguide and branching to two symmetric waveguide, gives 50% power, then again 50%, so ultimately 25%. And if we consider the insertion loss, what is the major component, and that should be theoretically just 9 dB, 3 dB, 3 dB, 3 dB, 9 dB. So in simulation it may be just about 9 dB. But the other parameters, important parameters, are the uniformity at the output, at the same time polarization dispersion loss there, because whatever the material we use, depending on the material, the propagation for TE and TM both are different, so polarization dependent loss will be there. So these are the typical different type of splitter: single mode width according to the design, then expanding that, and this is the branching angle, and these are the two output points. Similarly, asymmetric two branch is possible, 3 branch is possible, and 1x n type of splitter can be possible. This is the one particular design, simple design, that we design simple single mode waveguide and then branching to two direction. But here the points are, these corner points are the maximum scattering points. So that's why we have to go for this expanding type of waveguide without exciting the higher order modes. So these are this tapering waveguide, and after that we go for this branching. But again, for the technology point of view, if we go for the fabrication of mask and fabrication of this type of device is difficult, particularly when this branching starts from zero distance. So although it gives best simulation result, but after fabrication it may give quite deteriorated result. So you have to design for the technology compatible, according to the technology compatibility. So as per the technology, we have to have some gap where we have to start that, and we can fabricate the device. Similarly, these are another splitter based on multimode splitting. So this is a multimode interference splitter. Again, single mode, waveguide is stopping, expanding, and this is the area where mode conversion is there and super mode formation is there. And in this area, the interference occurs, and depending on the length, this type of standing wave pattern is generated, and from this maximum point, so we can take the output. So these are the length for particularly multimode splitter, and you see this length is inversely proportional to the number of waveguide at the output. So if we want to increase the number of outputs, the length will be less. So that will be advantageous in this case. But this is again, wavelength dependency is one problem, and other problem is the uniformity. See, this is the typical output for 1x2. These are the typical outputs for 1x4 or 1x8. You can see the length is like that. 3 L pi by 16. In case of 1x16, 8, this is 3 L pi by 32. So as we increase the number of outputs, the length of the device will be less. But because of the disadvantage of non-uniformity and wavelength dependent, we can go for symmetric type of design. This is particular one design where the output is center to center 250 micron separation, 1x8. So we design first here, and then this one, and then last stage. and after that we concatenate those things to get 1 cross 8. Typical dimension is around 2 centimeter for 1 cross 8 splitter on silicon type of material. But again, this is the design with zero distance branching. So best result you can get. So this is typical simulation where 1 cross 8 outputs are there. These are the different outputs. C insertion loss is just above 9 dB, 9.19 with non-uniformity of 0.08. Non-uniformity is the difference of the average from each individual. And these are the fabrication results, and you see that we haven't taken that technology compatibility. That's why these are the design parameters. So here the insertion loss is around 8 to 10, around 9. However, after fabrication we are getting around 16 to 21 dB losses for TE and for TM also. Similarly for non-uniformity, this is the simulation result, this is the after fabrication, and the polarization dependent loss. This is the difference between TE and TA. So that's why we can or we have to go for this technology compatibility. We have to consider with a little bit gap there, so that we can minimize the gap between design and fabrication results. Similarly, other type of design is also possible, that segmented splitter type of things. So here it is also with technology this is also possible, but it gives better result. So this is the typical structure after fabricated the device. With silicon platform we deposit thermal oxide with a lower refractive index around 15 micron. On top of that, the guiding layer of germanium doping, and after several processing, these are the typical waveguide we can make, and after that we go for BPSG, borophosphosilicate glass based top cladding. Again the refractive index is almost similar to this undercladding, so that the total internal reflection happens and the light is guided through this region. But after the processing, we have to have some annealing process, because after this deposition there are nitrogen hydrogen bonding second harmonic, and for silicon hydrogen bonding third harmonic. The insertion loss in the region of around 1300 to 1500, which is very much crucial particularly for communication, the loss is much more. But if we anneal those samples only at 1000 degrees centigrade for 3 to 4 hours, then insertion loss comes down, and because of the breaking of these bonds. So you see that after annealing, the insertion loss comes down. So this is a typical 1 cross 8 splitter we fabricated at Siri, and it was packaged at Samir Mumbai. And after that we can test and characterize with the use of C plus L band amplified spontaneous emission light sources. Similarly, I just give you a brief idea of multiplexer, demultiplexer also. That also has been fabricated at CSS Siri. So again, it can be asymmetric device or it can be symmetric device. Particularly here, we can see that this symmetric device with n number of input, n number of output, but it can be used as 1 cross n demultiplexer or n cross 1 multiplexer also. Here, these are the input, and these are the mode mixing zone. And after that, this added waveguide, this forms as grating, because the delta L increment of path difference is there, and that creates a phase difference at those points. And after that, again, this mode mixing zone. So each particular, according to the each particular wavelength, that will be constructive interference happens, and each individual wavelength will be separated there. Okay, so I just explained this is the principle of operation, and you see after this all the, as per the wavelength that will be focused in this output, and those wavelengths can be separated out. So this is a typical design of that. Inputs, mode mixing zone, array waveguide zone, and mode mixing zone at the output and output ports. It's like that. And this is a typical simulation output. These are the 8 outputs. This is the fabricated device. We have fabricated CSS series. Similarly, waveguide gratings can be used as filters. So this is a typical structure. We all have heard about fiber Bragg gratings. This is very much popular, and without fiber Bragg gratings now any optical system hardly can be imagined. But here we are discussing that waveguide gratings in the same fashion. Instead of writing gratings on top of optical fiber core, we can write in that waveguide here, and we have the advantages over material selection, at the same time structure of that material. So we have the possibilities of other very much useful areas of sensing, at the same time signal integration. So this is the principle, and the resonance of wavelength is depending on this equation, where N0 is the effective mode index of the fundamental core mode provided through that, and Nm is the effective index of the cladding modes depending on the mode we are considering. We have also fabricated, designed as well as fabricated. So in the design itself, we can design the phase diagram where the grating periodicity and the resonance wavelength we can plot, and from the grating periodicity we can simulate what is the resonance wavelength. So depending on the requirement of the resonance wavelength, we can design the periodicity. And here you can see that dual resonance property. So with the same periodicity we can get to the resonance wavelength that can also be optimized. The intensity at the same time, the wavelength of resonance can be optimized. So this is that particular device, and we can test with TE as well as TM modes for different sensing purposes also. In addition, we have fabricated lasers also in CSS series. We are not discussing too much on gallium arsenide, I guess, particularly 980 nanometer laser. It is being used for erbium loop fiber amplifier pumping. These are the laser bars. IV characteristics where we can operate up to 300 milliampere of current, which can give around 160 to 180 milliwatt of power output. We have also fabricated detector, indium phosphide based detector that can be used. Towards some future trends, we can extend the work in that fashion also. Whatever the passive, I have focused in passive components only, that's what I am discussing. So whatever the waveguide gratings we have fabricated, that can be used for switching applications also. So with the same cladding and with the same periodicity, that can be used as switching. So at resonance, it can be switched on to all the waveguides. When it is not resonating condition, it will be off, like that. Similarly, that waveguide gratings can be fabricated in different polymers also, like a benzoyl-butane or other epoxies, where thermal expansion coefficient is much more. So thermal tunability will be much more, so that can be used for temperature sensing and other applications. It can be fabricated for thermoptic gratings, and that is dynamically controlled. So on top of this, we go for that metal pad type of structure where we can send some current. So according to that flowing of current, some power will be generated, and that gives some temperature heating, and that heat gives the refractive index changes in the overcladding as well as guiding layer, and that gives this refractive index modulation, so which gives the property of grating structure. Similarly, that gratings can be written by using lasers also. Just like writing fiber Bragg gratings, you can write these gratings depending on the photosensitivity of the waveguides. So those are the possible areas. In addition, there are other interesting areas of photonic crystals. So depending on the structure and hexagonal structure or rectangular structure, we can design the photonic crystals. And that is having the idea concept of creating band gap in that plane. So that gives a band gap of propagating the signal in that plane. So after a formation of symmetric waveguide, if we go for line defect, so within that band gap we can send one particular signal without almost any loss. Similarly, we can create a point defect to create a quantum dot type of things, and that can be used for different applications. In particular, for our LED fabrication, we are using this concept that we are fabricating gallium nitride based LEDs on sapphire substrate. The refractive index is 1.7, 2.5, and after that air. So whatever the LED light is being generated through that quantum well in that region, that will be trapped in this material itself through total internal reflection. And that gives the deterioration of the property in terms of heat dissipation, because light is being trapped within that material. So if we go for photonic crystal structure design and fabrication of that, depending on the light emission, particularly blue light is emitting around 460 to 470 nanometer. So if we design that photonic crystal structure in the form that it creates the band gap in that region, so light will not be providing in that direction. So instead of providing in that direction, light will be extracted out in that way. So that is our basic objective. And in that way, researchers are doing, and more than 75% extraction efficiency can be improved. Similarly, this type of structure can be used for biomedical applications also. So this type of structure, here we can use some sources, here some plate for sensing layer, and so we can go for online biomedical sensing applications. So these are the areas we can carry forward our work. So we conclude that overview of integrated optics is given. Some basic passive photonic components we discussed, and just outlook of present activities of photonics has been given, whatever we are fabricating at CSR series, and some future trends. So with this, I thank. If you have any questions, we can discuss.
So Dr. Pal has given a very comprehensive view of some very interesting research that is going on at Seri Pulani. And if there are any questions that probably you would like to answer, if not now, maybe over a lunch. Yes, Dr.
One
Shah.
question.
Yes.
This optical communication, what is the system taking care for modulation, demodulation, whether multiplexers and multiplexers serve the purpose, or some other devices which we can use to just superpose the intelligence over the optical wave?
This is, I discussed that multiplexer, demultiplexer, this is the passive type of. But in addition to that, I think what you are discussing, that is active type of modulation. So that can also be interpreted that in the first diagram itself, what I have discussed within the planar diagram itself, if you have some waveguide that is having some active possibilities, just like propagating of signal, and if you go for some modulating structure on top of that waveguide as well as the bottom of the waveguide using different material, you can modulate the signal propagation by any means. So whatever the signal is being propagated through that waveguide, you can modulate, that can give that modulation.
So in case there are no more questions, I would like to thank Dr. Paul for his very interesting presentation, and then this session then comes to a close. Thank you, everybody.
Thank you.
Session is Dr. D.C. Dubey. On behalf of the IAS fraternity, I would like to express my deep gratitude to Dr. Dubey for accepting our request to grace the occasion with his benign presence. With 35 years of experience of teaching at IIT Delhi, Dr. Dubey has also worked at several international laboratories of well-known universities such as Pennsylvania State University and Swiss Federal Institute of Technology, Switzerland. Currently, working on microwave processing and advanced materials, Dr. Dubey has written more than 100 research papers in international journals and has authored 2 books, namely Electronics, Circuits and Analysis, and Microwave Devices and Applications. We welcome you, sir. May I now request Professor K.S. Sharma to accord a floral welcome to Dr. Dubey. Thank you, sir. May I request Dr. Dubey to kindly take his seat on the dais. The invited speakers for the session are Dr. S.B. Chakrabarti from ISRO Ahmedabad and Professor J. Bihari from Delhi. I would now request the chairperson to take over the session.
I welcome you all in this session of this conference. The next invited speaker is Dr. Chakrabarti, and he is going to talk Dr. Chakrabarti has 19 years research experience in computational electromagnetics, microwaves and millimeter antennas. He has served as the German Aerospace Center DLR during 1999 and 2000 as guest scientist deputed from ISRO. 60 research papers published in international research journals, has received INSA Visiting Fellowship in 1996, shortlisted for INSA Young Scientist Award in 1997. These are briefly his achievements. And now we will listen on this topic. And the topic is microwaves in Earth observation. Dr. Chakrabarti.
Working on the antenna, the development of antennas for microwave sensor, different type of microwave sensors. So basically in this presentation, maybe you will find more emphasis on the antennas rather than the science details of those sensors. So just to start with, next slide. Just to start with, what is needed for the observation? So generally it is very simple question. What I need the light, that is the light reflected from an object on my retina, then only I can see an object. But can I see anything in the darkness? And there the answer is the microwave. So using microwaves, that is all these microwave sensors, they all weather in the day and nights. They can operate without the light. So what are the principles? I will just go through that, how the microwaves are useful and what are the different types of sensors, and in the context of ISRO, what are the works going on, so that I will highlight in this presentation. Now what is microwave with earth observation? Now as I told in the morning that any object, if its temperature is above 0 degree Kelvin, it radiates, that's electromagnetic radiation. So either it can be at self-radiation or otherwise also it can be illuminated by a microwave source. And then what is the scattered microwave energy? It can be received by a collecting aperture, and that collecting aperture is nothing but our antenna. And then it can be fed to a detector to detect the signal, and from that detected signal the properties of the objects it can be retrieved. Yeah. Now these things are widely just said. I will just skip this slide. Now just I'll say the micron in microwave. So this by micron in microwave we don't understand the way microwave understands the small wavelength. It's not a micrometer. The wavelength are in the centimeter only. So and this frequency, whatever this infrared light and the frequency, these are a little bit arbitrary. And there is a change also. What is the band? So depending on the application and depending on the standards, there are changes. So there is no fixed boundaries. There is this band is this is the frequency, this is the wavelength. There is no fixed boundaries. This is already been covered. Just I like to say that these bands are very arbitrary named. Like you see, it is coming L band, S band, C band, X band. There is no chronological order. Logically, it should have started with A, B, C, D like that. But so the reason is like that. These were used to confuse, because you see that microwave started because of the wire time. There is the World War II. So this is basically to confuse the enemy. So basically all these were the military band, L band, S band, and K band during the World War II. These are the secret codes, so that you do not know what is the frequency. Of course, after that they were declassified and this K band, millimeter band were added after this. Obviously, there are some this thing like this band. No, K band is in between. You see the K band, then KU. So K it is under and this is the above. So this way also it can. But basically, there are no logic why it is called X band and Y L band and all this. Now, why microwaves and earth observation? It is because of their longer wavelength. Because microwaves, as compared to the optics, it is very much. Suppose if I consider a football is the optical wavelength, then it's the football ground is your microwave. So it's such a difference. So the difference is there. So since their longer wavelength, the visible and infrared, the microwave have some special properties. What are those special properties? The special properties are this. One is the Doppler frequency shift. This is one of the very important, and then the polarization change. So, and it is absorption as well as scattering. So these are the properties that is used in the sensors to know what are the properties. Now, an object, if it is illuminated by a microwave signal, and when I analyze or when I detect this scattered signal, it will have either a Doppler frequency shift, or it will have a polarization change, or even there may be a frequency. What I meant to say that this polarization and the frequency shift. These are the two important characteristics by which the targets can be retrieved. Now, microwaves are able to penetrate more deeply into visitables than optical waves can. Like soil moisture and all these things, it is possible using microwaves only, not the optical signal. And as I said already, this probably allows the detection of microwave energy under almost all weather and environmental conditions, so that the data can be collected at any time. And microwave remote sensing, that is that if I compare it to the optical like camera, these are possible in a good weather condition, in the presence of light, it is possible, but this is not possible. That is the sea-wind vector. Sea-wind vector, it is possible only with a microwave sensor. That is called I will come to that sensor, that is called the scatter meter. That is only possible when you use a microwave remote sensor to study the sea wind. Now, as I said, the frequency characteristic, Doppler effect, and the polarization and the backscattering, these are the parameters used to derive the geophysical model of the targets. So, as I said, this is a day and night all weather except during the period of heavy rain, because heavy rain, what will happen, this micro signal will get attenuated, too much attenuated, so that the dynamic range will deteriorate in such an extent that retrieval of data is not possible. And it gives you a complementary information in the optical and complementary information means that is in the bad weather or in the dark, in the day and night operation, night operation. And we have that is, sensors are two types, that is the passive and active, that will come in detail. And this is the absorption characteristics of two molecules, that is one the oxygen molecule and the other is the water vapor molecule. So you see there are some frequency bands where the absorption is very high, and these are the frequency band of interest. Next please. I can do that. So these are the types of microwave sensors. So it is passive sensors and active sensors. So in passive sensor comes the microwave scanning radiometers, and it is non-imaging, nothing looking, it is a fixed radiometer, that is not a scanning type of radiometer. And in the active sensors where a microwave source is used to transmit a pulse, to transmit a microwave signal, and then the microwave signal echoed or scattered by the targets, it is received and analyzed. So there are again two types of, that is the imaging and the non-imaging. For imaging type, it is there are two types of, basically the active sensors are the radar types. So we are having real aperture radar, side lobing radar, then airborne radar, and synthetic aperture radars. So what is